everyone, it's Judy Warner. Welcome back to day 3 of our DesignCon tailgate party. Today we'll be pre-gaming with the Silicon Valley startup Avishtech. Lee Ritchey, who has been closely associated with technology, has actually endorsed this product because he believes the time has come to be able to characterize and simulate PCB stack-ups so you don't have to play whack-a-mole in troubleshooting your designs once you've built them and populated them. We're going to have a really robust discussion about why this is important, and I hope you will go see them at their booth at DesignCon. I hope you'll enjoy getting to know these up-and-comers, and we look forward to seeing you at DesignCon. Now let's jump into our conversation with Lee, Keshav, and Tarun. Well, hello, gentlemen. Thank you so much for joining me today. Why don't we first start by introducing all of you to our audience. Let's start with you, Lee.
My name is Lee Ritchey. I'm president of Speeding Edge, a consulting company, as well as a training company. And my background is microwave engineer originally on the Apollo program. Happened to be in Silicon Valley when it began to be Silicon Valley. And I went from there to designing supercomputers, which is kind of a leap. And that's where we had to drive the technology, meaning materials and board fab and that kind of thing. And early on, we only cared about impedance. And of course, that long ago, it hasn't faded in the background, but it's not the hardest problem to solve right now with materials. The other things that are an issue, and this has to do with really stack-up design, which is what this tool is all about. Originally, we only worried about impedance, and most everyone let the fab shop do that calculation because it was easy for engineers to put that task on the fab shop. And it worked okay, except that as time went by, we demanded more of the boards than just impedance. And right now, where we are is we worry about skew and differential pairs, loss in the path. A big driver is power delivery, which means that the stack-up has got to be more carefully engineered than in the past. And most of the things that we're talking about here, the fab shop could never help you with. And so and I teach my classes, I tell the engineers that you have to take charge of stack-up design to make sure that all these things are accounted for. And that then causes another problem, which is we used to let the fab shop worry about manufacturability. Things like resin stop and do you have enough resin to fill the voids in adjacent layers and all those things. Well, if the design engineer is doing the stack-up now, he's got to worry about manufacturability. And that means you got to worry about, are your vias going to fail? Are you going to have enough resin? That kind of thing. And that's kind of where this tool comes in. That's the reason that I'm interested in it. There are lots of ways to design impedance, but there's only one that helps you with manufacturability. And so that's why I'm kind of a part of this picture, is because now we engineers have got to worry about that. We need a tool that helps us. That's who
Indeed.
I am and what I do.
What you're up to. Okay, well, Keshav and Tarun, you are obviously the founders and developers of Avishtech's technology. So, Tarun, why don't you introduce yourself, and then I'm going to come back to you and ask you, just do your intros, and then I'll come back and then ask you to dig deeper into the technology. Tarun, you kick off.
Yeah, so I'm Tarun Amla. I'm the co-founder and chief technology officer for Avishtech. I've been in the industry for over 3 decades on the materials side, and before working full-time on Avishtech, I was EVP and CTO for iTech. I developed their products, which is one of the largest material suppliers for the PCB industry. Before that, I was CTO for Shanghai. And before that, for a long time with Isola, which was previously Allied Signal Honeywell, as their CTO for their laminate business, for copper clad laminate business. So as far as my educational background, I'm a mechanical engineer. I hold a doctorate in mechanical engineering, but I've also got a master's in electrical engineering from Stanford, and and an MBA as well. But I have a strong emphasis on computation in computational mechanics, which I did from Purdue, and modeling and simulation. So it kind of dovetails with what basically led to the creation of the software is the materials synthesis of materials background, computational skills, and of course combined with Keshav's background. So I'll turn it over to Keshav to introduce himself.
So I'm the founder and CEO of Avishtech, and my background is that I'm also a mechanical engineer. I did my undergrad in mechanical engineering from Caltech before starting my graduate work at Stanford. I completed my master's in material science and engineering there and was working on my PhD in mechanical engineering. But I left the program to work full time on our Gauss offerings from Avishtech, and we'll dig a little deeper into all of that. But basically, as Tarun said, between our backgrounds, we were able to really approach this, and we were uniquely qualified to do this because of basically the major problems facing the printed circuit board industry require synthesis of several different disciplines, and we had that background that was necessary.
Well, I always love when I hear that message where the rubber meets the road, which is where I think Avishtech is one, I'm always keeping my eyes on innovative companies like Avishtech because there are so many disconnects in the disciplines that, as you all know, we have all the scars to prove it, right? And I love the idea that you're bringing some of that intelligence to engineers. So Tarun, as you know, 30 years in the industry, academic creds, but, doing all the work that you did, what was it that you sort of observed that were pervasive problems, specifically around materials and the way stack-ups were being modeled or not modeled?
Yeah. So like I said, I've been in the industry for a long time. The main issue that I saw was the way the design process worked. Just to look at material selection alone, it was a highly frustrating process, and this was so onerous. It could take several years. In most cases, you'd find out that simple things, just the stack up itself, could lead to failures and in the qualification process, and that was something that I always felt that why can't that be modeled? Why can't that be simulated? Because if you could, then there'd be a lot of heartache and other issues you could avoid just by following that simulation process and then making sure that your design worked. Like Lee alluded to glass top. That would be a major issue in most of the cases. CAF, that could be avoided just by simple tweaks to your stack up and by the selection of the proper materials. And then there were other things like thermal reliability, and so these are the things that are not looked at right at the outset. So look at impedance, then you say, well, it's off to the races, but that doesn't work because the board that has to satisfy a function has to also satisfy other requirements. And so we thought we needed a holistic approach to design process, and that's why kind of led us to look in this direction and try to figure out how this can. And it's a pervasive problem. It's everywhere, and the process is such now that the level of frustration is so high that they test it, build boards, and accept it when it passes. So you might have 7 or 10 failures prior to that. The moment you get a success, you run with it. So which is not a very reliable way of doing things. And especially now, there is very little margin for any of these things. And so very subtle changes in your stack, in your materials, in your processes can lead to major problems. And it's hidden because nobody talks about it. When you look at semiconductors, yes, anytime there's an issue, people hear about it. But this is kind of approached as the cost of doing business. And it's kind of expected that it'll take that long. So now what we're trying to do is upend the whole process and work with the software. So that basically led to the development of this software and the software products that we have.
Okay.
Yeah, and basically, you know, basically a big issue that you see in the industry is that, you know, whatever your particular silo may be, you're looking at that particular aspect of things. So you may be looking at the electrical aspects or the mechanical aspects, the thermal aspects, whatever it may be. But the problem in the industry was that a failure is a failure. It doesn't matter if it's in your particular domain or in something you're not an expert in. If you're having board failures, you're out of pocket, and basically your project can't move forward. So that's where what we basically said was that we wanted to bring this product to the market so that the designer or the engineer can have visibility over all of the key aspects that really matter. And basically, they don't have to go in and try to develop their own background in these other disciplines. And it basically enables a multidisciplinary approach for folks even working within their particular domain of expertise. So, you know, an electrical engineer doesn't have to also be an expert in mechanical engineering or material science, chemical engineering. They can just go in, specify, you know, what are they looking at, put together a stack up, and figure out, well, okay, is this going to work for all of my different requirements or not? And you know, they'll be familiar with what the requirements are, but they won't necessarily have a good feel of, well, how do I get there if I'm not there yet? And so uh, the biggest thing was that, you know, in the semiconductor industry, they'd gone through this process a few decades ago. It became absolutely critical to have this, you know, software based verification process. And so they'd run simulation, and basically that was a key gate before you could ever move forward. But the PCB side didn't really have this. It didn't ever really happen on the PCB side. Uh, like Tarun said, they kind of accepted it as the cost of doing business, and they could kind of absorb those costs for a period of time. But over the past decade or so, it's gotten to the point where that's just not really practical. It's really become prohibitive. Uh, but you know, without software solution, how are they going to really adopt this system level approach? And so, the first step of that is for there to be an alternate way, to be a proper way to do it. And basically, that's what we said to develop. And main reason that, you know, a solution didn't come out in the past is that, you know, the the basic challenge with these kinds of with this particular problem, the PCB problem, is that it largely comes down to the fact that the materials are composites. You know, with semiconductors, silicon is silicon. You know, the same grade of silicon has the same properties every time. But these dielectric materials, you can have something that you call material A, but it could have 40, 50, or 100 different configurations in the prepregs and cores. And so it's not feasible for anyone to go in and characterize each of those separate sets of properties. So you need sort of a different approach. And that was key to what we built. And now that, you know, this option is available, we're seeing a lot of customers are gravitating toward it because they do want that system level design approach. They don't want to be spending you know, significant amounts of time and money building, respinning, and dealing with all of that chaos. They'd much rather a cleaner process. And so that's where we kind of filled that need.
Okay, I want to ask you more about that, but first I want to toss it off to Lee and say, Lee has been, excuse me, in high-speed electronics forever, right? Always out on the leading or bleeding edge. And Lee, why do you think that the semiconductors, as Keshav said, hearing these words, characterization, modeling, simulation at the material level is sort of mind blowing. Lee, you've been around that your whole life. Why do you think that is? And why is this? I know this is the first product you've ever endorsed in your career. Give us a hint of that. And then, Keshav, I'm going to come back to you and ask you some specifics about how the software works. Okay, Lee.
To sort of add to what Keshav has said, the reason the semiconductor industry did it and we didn't is, as an example, the integrated circuits we put into the first terabit router, a mask set was $500,000, just the mask set.
Wow.
And so if it's wrong, you get to do that again. And so cost drove that. And it was cheap to spin a board for a long time. It's not cheap anymore. As an example, if you build a server board, the components on the board are often $30,000 or $40,000, just the parts. Forget what the board costs. And if it's wrong, you throw those in the garbage. So we have reached a point where finally we can't afford to be that careless. I mean, and the other number that is not, and we're not good at our cost accounting. Everybody ignores the fact that when you spin a board, everybody in the development team and sales and marketing sits on their hands while you get the next board, and you still have to pay them. That's a sunk cost. And I have often used that to illustrate to my clients why it's right to do this extra work, because it's economically a good bargain. And that's what leads to me liking this tool, because we need that as part of developing Stack-Up. Again, I have to do the Stack-Up now. The fab shop is not doing it. And that means I'm in charge of manufacturability. That's via reliability. It's all kind of things that have to do with how you build the board. And this tool helps with that.
Well, you're right. And how many electrical engineers that are 40 years old know much about manufacturing these days? Like Lee, you and I have been around, and Tarun, we've been around long enough that we had to go to plating rooms and talk to fabricators and stuff. But now we have EEs laying out boards. And so there's all these layers of complexity that makes this a particular mess. But to your point, it's not cheap to respin a 32 layer board either, much less all the cost of the parts. So I see all the moving pieces. Well, I'm really excited about this, and I've been watching you guys for a couple of years. Okay, Keshav, tell us a little bit, without giving away your secret sauce, what Gauss is actually measuring. And you mentioned about the varying materials. So how does Avishtech address all those variabilities and thickness, composition, and all those type of things?
Exactly. The biggest issue historically is, even if you say there's an alternative way of doing simulation, and with some more traditional general purpose kind of approaches, the problem is always, where do you get the properties from? Even beyond, the fact that those general purpose approaches aren't well suited to this kind of analysis. If you do finite element analysis, it can be a multi-year project. Even if you know all of the inputs, have all the data, still going to take you a year to handle all of those issues. But that assumption that you have all the inputs, all of the data that I just used right there. I mean, how do you get it, right? Because even if you're working with the materials vendors and moving in that direction, you're not going to be able to characterize that, because what are you going to do? Just run every single configuration through materials testing? That's not practical. And even then, there are a number of properties that simply cannot be measured in any practical sense. I mean, so if some of these, just in terms of the kind of samples you'd have to prepare, it's just not something that you could ever make, and each one might take you several months just to fabricate, uh, and get going in that direction. So and you'd have to develop your own methods. So what we did was we looked at the problem in a different way, and we said, well, how can we go in and take that mystery out of it, take it so that both sides of this challenge we address. We address the actual simulation side in terms of how do you actually have a simulation environment that's able to give you results that are accurate and provide those results quickly without you needing to have a PhD to set it up and interpret the results. Uh, but also at the other end, uh, how do you have something where the user uh, is only having to provide information that they know? If they just select, this is the material I'm using, these are the constructions, put their stack up together, that should be it. They shouldn't need to tell me, what material A or B, what their properties are, and all of that. And so that's where we built this, engine that extracts the properties, and we've got that fully resident in our library, and so then it conducts these simulations and accounts for all of the different configurations, all the different resin contents, glass styles, and the each individual resin, and then basically figures out the properties layer by layer, uh, accounting for all of that, all of the different components, and then also at the board level, uh, basically accounting for all of those layers. And then once you have that, you can move forward to the real results that you actually care about, which we then that's where we kind of take it to the next step with that.
So, as you guys have met with customers, well, first let me back up. Does your tool also take into considerations, Lee had mentioned a Microvia reliability, which is a thermal issue. Does it take into consideration the way materials behave in that respect too?
Yeah. So that's exactly what we did. So what Keshav was talking about was, how do we get to the core, which is, the models for the materials. And that's what we take, and then we kind of simulate the entire board. So properties may be available layer by layer, and they're limited, first of all. They're not accurate. But with what we've done with our modeling, we've been able to do this, and we've been actually able to go back. So you'd be surprised at the number of material suppliers are our clients, who are actually working to get their computations and their measurements verified by us. So that's what they do, is they come to us and say, well, we want to measure these properties, and how do we do that? So that's the kind of level of credibility we've
Amazing.
gained. But to your question about Microvia reliability, thermal reliability, those are all built in. So what happens is we simulate it. Let's say we have to simulate a thermal excursion, we'll do that. Thermal cycling, we'll do that. And then basically what it does is it's subjecting the board to those kind of conditions with the Microvias, whether they're stacked or staggered. And then we just use the physics at that point in time to point out whether it's going to work or not, and how many cycles it will take. So those models have also been built by us. So in the case of Microvias, there was a study done, I think, by IPC back in the 80s, where they did round robin testing for plated through hole reliability. And so that's something that was done like 30, 35 years ago. But there's nothing like that for Microvias. And what we had to do was actually build those models and built those so that they could be fairly accurate. And that's what we've seen with our customers, that they work very well. So the Microvia, for instance, we say if you've got stacked with this pitch, this kind of an excursion, how many cycles are you going to get? And so we give a number, which they can then calibrate with their actual testing or the historical records that they have. And that's how we've kind of built a lot of confidence with our customers. So Microvia is a big deal. And like I said, there's nothing available in terms of models which you could use, but we actually help develop those, and they're all resident in the software.
That is amazing. We all love and work with Gerry Partida at Summit, and I know he's like the evangelist about Microvia reliability and sits on that. Have you guys worked together with Gerry on this on a functional level?
Yes, I mean, so we've worked with Gerry, and maybe Keshav can speak to that because he's been interacting a lot with Gerry, and Gerry's published a few papers where he's actually mentioned our software or
Some
at least
insights
the
from
use
it.
of.
Yeah.
Will you guys share that paper with me?
Yeah, absolutely. We can certainly send that to you.
Okay, that'd be great if you'd share that with me. Keshav, did you wanted to add to that? Or the other thing I wanted to ask you about is kind of where the rubber meets the road. If you can, again, with protecting everybody's IP, if you can give us practical examples of where this has been helpful for your customers.
Sure. Yeah, and so just to continue on the point you brought up with Gerry. I mean, Gerry's been great to work with. He's been one of our early, really very early adopters. Actually, we've been engaged with him for pretty much almost since the beginning, and he's been a big he's not been too shy about talking about how much he likes our software too, but also he's been a big help in giving us more and more feedback in terms of, hey, it'd be great if you guys could also look at this, and so he's been one of the really helpful customers of ours in terms of expanding what all we can do. And so, yeah, it's been great working with him, and that's the whole thing. The level of support we're seeing from the industry for this is largely a result of the fact that this is something where there was a pent up demand. I mean, people had been people in the industry. They've been wanting a better way to approach these things, and so when they see something come out, they see it as, well, this is my opportunity to help move this forward and help help basically improve the industry, and that's what I think all of us really are trying to do. So, I mean, to that end, to your other question about some examples, one example is there's a printed circuit board manufacturer. They licensed our software and been working very closely with us. So for them, the biggest factor was Microvia reliability, and that was the biggest thing they were interested in. And so they wanted to be able to use our software to tell their customers if a design is going to be safe or not. And if it's not going to be safe, their hope was that they could then recommend modifications that could be made. Either if you have the ability to increase the diameter here of your via, or if you can change to this prepreg instead of the one that you're using, whatever that recommendation may be, that's what their goal was. And so they've adopted a new process where anytime an order comes in, the first thing that happens is that it goes through Gauss Stack, gets simulated, and then they engage with their customer to tell them, well, this is okay, let's move forward, or I'm seeing red flags here, and they've said that historically there'd be times when they'd get an order from a customer, and their gut would tell them that this seems kind of iffy. I don't know if this is going to work, but they had no way to validate their gut or so there'd be times when maybe their gut is saying this seems risky, but I don't know, and maybe it was still okay. But the main thing was that until they went to actually go and build it, they didn't have any way to really validate that and determine what's real, what's not. Uh, and there'd be times when maybe this was the other thing that when they would make sort of their first prototype lot of it just to see, well, is it working, make the coupons. uh they'd only do a couple or three. There'd be times when it would pass those coupons, but then when they go to actually build it, they might still see failures, and so they were really unhappy with this process. But now, when they go and talk to their customer, they're also not speaking just from their gut. It's something that their customer can also uh, take in, and they say, okay, well, they send the results from the simulation. They say, I'm not confident in this design because Gauss is predicting it's not going to survive your requirements. Maybe it's not going to survive the 6 reflows at 260 that you need. And their customer says, oh, okay, well, so what is the simulation saying? What's it saying it can survive? And then they say, okay, so then is there a configuration that gets me over the line? And there's a lot of contentiousness that's left this process, and they're basically able to move forward a lot faster with designs that really work. And they've had times when projects that would have been halted for inordinate amounts of time are able to move forward very quickly because they find a better way of doing things, and so they're not running into these failures. And this customer, they've done extensive validations on this, and they've been able to extend this to new insights, like that the impact of pitch, for example. Wider Their gut was that wider pitch might be leading to higher reliability, but through their use of the software, they realized, well, no, it's actually the opposite, and the reason for that is that the gut feeling is more in line with what's happening to the dielectric, but the copper, the vias themselves, they're actually getting more and more reliable. And so that's one example of a customer, and I think Tarun had another that he had in mind.
Yeah, I think the other one is this was another use case, and at the customer end, they were building these boards, and I just want to make sure that everyone realizes that this is not on high-end designs. This could happen on standard 10, 12 layer boards, and not necessarily very high layer count boards. So these people might think they're plain vanilla designs, but this case study actually told us that very subtle changes that people make on the stack ups could have major implications. And in this case, what was happening was that the customer was seeing pretty good solder joint reliability, and then suddenly on the next iteration, a minor change that they thought they made, they were getting only 50 cycles. So kind of thought it might be warpage, and so asked us to kind of look at it. And when we did so that's the kind of stuff that we do when a customer approaches us. We do proof of concept first, and then once they become believers, that's when we kind of make a sell. But now it's kind of, that process is becoming kind of is shorter now because there's a lot more word of mouth out there. But so we did that. Those simulations found out that warpage shouldn't be it because it was just of the order of a few microns. It wasn't significant enough to cause the kind of distortion that would cause these kind of failures. So, but our software was telling that they're modulus, and that's something that people don't talk about in our industry, is because modulus is kind of, why would you talk about modulus of a board? It should be kind of in the same regime as your laminate or pre-preg, but it's a composite, like Keshav said. You got copper, you got resin, you got pre-preg and glass, and all those things together. So we found out that their modulus had moved up by 25%, and that was exerting higher stress on the solder joints, causing it to fail. And this was just adding 2 layers of 2-ounce copper. And that basically did this because it made the board much stiffer, and that was exerting more stress on the solder joints. So then, of course, the conclusion was that they probably needed a high shear strength solder joint, high temperature solder, and then we also developed models for it. So kind of in the end, it addressed the problem, but this was discovered like 18 months out. When the design was out for 18 months, because they started seeing these failures. Because you don't test for solder joint reliability when you build your board. You test it for maybe plated through holes. You test it for your electrical functions. But then when the rubber actually hits the road, when you're making the production runs, that's when they started seeing these kind of failures. So it was like 18 months down the road, and then you just send SWAT teams out there trying to address it, whether this could be addressed. So it was a pretty satisfying case study for us.
That is really, Go ahead, Keshav.
Sorry, go ahead.
I was saying this is when engineers start playing whack-a-mole, right? Because it's something that's out because we're like, oh, we're at solder joints and and it's this and this and this, and they start hitting it, and then like Tarun said, and then it's like, don't everyone move, we got it to work. Okay, it passed.
Right.
And then to Lee's point, then the marketing people are like, finally, and this whole crazy cycle starts again. I'm sorry, Keshav, what we're going to say, and then I want to wrap up with Lee.
No, so I was just saying that, and that's the big thing, that it's a lot of our customers kind of come to us when they're in that mode, where they've first had a crisis, but now of course we're seeing more and more people who are saying, well, why don't I just go to a better way of doing things, because as that word of mouth is spreading, and so I mean, on the thermal side, the reliability issues, those have been a big thing. But we've also had, some folks who are coming to us for things like skew failure. I mean, there was a customer who had basically been dealing with their skew problems by kind of restricting themselves to one particular material and 2 different glass styles within that material, because they'd done hundreds of different design tests on those particular configurations. But of course, that process, that's very restrictive, and so they were now getting to the point where this just wasn't practical for them to continue. And so, just as another example, on the signal integrity also is a major thing. And so they were looking for a solution and couldn't find anything, but they came across us. And so they got the software just for this particular purpose, because that was the issue they were facing. And so they found, within a couple of % of accuracy, we were matching up with the data that they had, and then so now they've adopted this as sort of their new process, that they'll simulate with Gauss, and figure out, well, okay, am I going to have skew failures, or am I going to have skew problems or not? And is this going to be within my skew budget? And so they're able to iterate through, and that's where I just wanted to bring up that example as well. And then the other point that I just wanted to make was that that's of course all the folks on dealing with issues that where Gauss stack is really what they need. But then, back to Lee's original point also, which is even at the basic level, every designer really should be able to handle the impedance side of things. Relying on their vendors to do that for them is becoming less and less practical for them to do. And so that's where, just another point to bring up is another piece of software that we've just launched is it's called Gauss PCB. And that's where we've developed something that allows every designer to basically be able to go in, at a price point that's reasonable for them to adopt as well, and they can go in, put together stack ups, and handle their impedance requirements, the basics that are really important. So we wanted to democratize that as well. So I just wanted to make sure to mention that as Tarun said, of course, Gauss stack. It's not only for the folks dealing with really high layer count designs, but Gauss PCB is for the folks who are even working on what might be fairly typical standard kind of designs. But even then, you need some environment that has the basic data you need, the ability to run impedance, and then look at loss, things like that. And so I just wanted to mention that as well.
I mean, who knew that all of these issues like mechanical stability, warpage, signal integrity, probably power integrity, thermal things would all come down to having really good insight proactively to your stack up, which is why I keep my eyes on you guys. And I know you're going to be at Design Con, and I really enjoyed this conversation, and I want to talk more. And I know I'll be seeing you at the show, so I'm excited about that. I wanted to bring it back to Lee and say, um, Lee, I know you're going to be with the Avishtech team at DesignCon, and you're going to be giving mini tech sessions. So first, I want to hear about your mini tech sessions so people can plug into those, and then I'm going to share links in the show notes for booth number and all that. And then, Lee, I'd like you to take us out and give us like the elevator pitch of why Avishtech Gauss Tech doing this work proactively. What's that going to do for design engineers?
Well, the mini sessions that we're going to be doing are basically an expansion of what I started out with here, namely talking about how we have done things in the past and why that doesn't work anymore because of the additional demands on a stack up that a fabricator could never help you with. And the purpose of that is to convince engineers that you got to learn how to do the stack ups. Because you're the only one who can account for the things the fab shop does not know how to do. And once you've taken that responsibility, yeah, you're responsible for the boards being the right impedance. And this is the very first reason people object to this is, well, if they're wrong impedance, it's my fault. I can't give them back. Well, that's actually the easy part. That's the easy part. It's the other things that you have to make sure you get right. And Keshav mentioned one, which is skew. And so, because all those things are signal integrity driven, they have to be dealt with by the design engineer. And so, the manufacturability, which the fab shop used to take care of, no longer sits there. It sits on the desk of the design engineer, who has to worry about resin flow and via reliability and all those things. In other words, get some skill at manufacturability. And of course, I've been in probably 250 fab shops, so I got a good idea how that all works. Design engineers don't get to do that. So this tool, I kind of look at it. It audits my stack up to see if I got it right. Mm-hmm. That's what it does. It audits that and tells me, is there enough resin in the prepreg? There's a variety of things that it tells you, Z-axis expansion, all those things that you got to know about. And this tool points those things out to you if they're not what they should be, so you can adjust things before you build the board. As I said earlier,
Yeah.
And probably the saddest example I can cite in recent years is we had a client who wanted to fabricate prototypes in the U.S. and build volume in Asia, and we didn't want a handoff problem, so we picked ISU Pegasus, who has a fab shop in Southern California and one in Korea. And we did a great job of getting the prototypes all working correctly done and shipped off the design to Korea. And with the confidence that we had it right. And we released an order for 400 boards. And when we got back, none of them worked. None of them worked. This was a server card with, gosh, no, I don't know, $20,000 worth of parts on each board.
Ouch.
Scrapped the
Ouch.
entire order because of an error in the stack-up as it was handed off. I mean, we had it right here, but if the shop in Asia had this tool, they would not have made the change they made that caused this failure.
Amazing. Yeah, those are the kind of things. Yeah. So what you're saying then, Lee, is that you get that proactive insight that like will save your bacon like on 100 different levels. Like that's huge.
And of course, when I can, I tell my students that you need to have a direct link with the manufacturing engineer at the fab shop so you can bounce off those people what you want to do. Well, very few engineers have that. They don't
It's
have that.
true. And there's a variety of reasons. I always say, yeah.
Yeah, they don't have that link to the fab shop that I do. And so this tool is a substitute for that.
Which is great because who has the time these days? But I just love that it stops them from playing whack-a-mole later, and just crossing their fingers and toes and hoping it ends up good in the end. And, nobody wants to do that. So I think that's why I'm really watching you so closely and your customers. I've really enjoyed this conversation. I'm positive our listeners have too. I'm looking forward to seeing you all at DesignCon. And I actually didn't know you guys were that connected to Gerry Partida because he's my go-to guy. So that's really good. Will you please send me his paper and then I'll get your booth and all of that so we can send our listeners to more resources.
Well, the Gerry thing for me is he was one of my students starting about 30 years ago.
Yeah.
Yeah. So if there's anything that is not what you might want it to be, blame it on me. I've been his coach for a long time.
Okay, well, I'm going to blame it on you, but I always go to you too. So I feel like, okay, good. I have all the right people in my circle. Well, again, thank you guys. Have a great show. And I'll make sure, is there anything else you wanted to share with me before I let you go? I know you're so busy.
No, I think
I think we covered.
that covers it. Thanks, Judy. This was excellent. And looking forward to seeing you at DesignCon.
Okay.
Same here.
Thank you all. For our listeners, I hope you've really enjoyed this insightful conversation and you're as excited about this technology as I am. I'm going to put lots of resources for you in the show notes, so make sure you go check that out and make sure you go, if you're at DesignCon, make sure you go over and see Lee and Tarun and Keshav at their booth and see, you can see, I'm sure, the software there and see it in action. So thanks for joining us and we'll see you next time. Until then, remember to stay connected to the ecosystem.